Good afternoon. Welcome to lecture 137 and 138. Today on the course Thermodynamics of Materials. Today we will take up the points topic C, which is to show that Wagner's interaction parameter formalism, E formalism in short, is thermodynamically inconsistent. We went halfway or more than halfway, almost towards the end. We actually showed why this formalism is thermodynamically inconsistent. Taking an example of binary system AB, this was done, but still actually this was the last phrase that we used, the last sentence that we used, that we said here, that even so, although thermodynamically inconsistent, even so we can use this use this Wagner's formalism for dilute solution numerical problems. For example, steelmaking problems, there we can use this without incurring much error. One thing I tell you, that what is the reason that Wagner's formalism has been thermodynamically inconsistent? Because of the approximation that we made. We actually truncated the expression of activity coefficient, that we obtained from MacLaurin series. We actually cut out the drop out the what is this called quadratic terms. We removed this. We ignored these terms, but that has made this thermodynamically inconsistent. And why that was made by Wagner? Because for dilute solution, quadratic terms actually, like say xb square, when xb is very small, small, for example say 0.1, say, then xb square will be even smaller, 0.01. That was the ground for ignoring the quadratic terms and give the simplified linear form, and that is which is known as Wagner's E formalism. So it has actually a kind of setback, maybe, that thermodynamically inconsistent, but this is not very serious issue, serious mistake, because what is the reason? That the error that is incurred for that omission of the quadratic terms, this actually I said last class, that is the error that is with much error, without incurring much error, the error that is incurred is less than the experimental error. So that's why there is no problem. It may not satisfy this what is called thermodynamic thermodynamical consistency equation, but that doesn't make harm for our numerical calculations. For dilute solution calculations, that doesn't make any harm. That is because this calls for to be thermodynamically consistent, there should not be any error, 0% error, no error. But this incurs a little error, just little error, because of the quadratic term omission, and quadratic terms contribution is small because the linear term itself is small. So xb and xb square, mole fraction of b and mole fraction of b square. So mole fraction of b is small. For example, as I said, 0.1, say, then it is 0.01 xb square. So that can be ignored with respect to xb. So this is the whole issue. Now we will continue on this. So this also you don't have. I think you don't have any trouble, because this was the last few words that I wrote in the last class, and we start from this point. So what let us see. It is better to have this what is this called? Its impact. The impact of Wagner's epsilon formalism is more significant, is more pronounced when we consider a multi-component dilute solution ABCD quaternary system representing iron, carbon, silicon, oxygen in steel, just for example, any dilute solution will be actually treated with this formalism. Any, not necessarily steel, but steel is very important, okay, system for us. So, and steel is a dilute solution also. So we often use this, and we will actually have an assignment solely dedicated to steel making. Next assignment today will start. Okay, after an hour or so. Okay, so that let us see. After some time we will start. So let us see. First finish this, for example. So what you see, then what you get, ln gamma b is what? Ln gamma b 0 plus epsilon bb, because MacLaurin series, we did this for binary, but now for multi-component means 4-component system, quaternary. EBB XB plus EBC XC, E is epsilon BD XD, etc. What we have ignored? The quantity XB square, XC square, XD square, or XB XC, all such things, XB XD, XC XB, so on. So ignoring the quadratic terms as before. Ignoring the quadratic terms as before. Okay, so this. Next is similarly ln gamma c is what? Ln gamma c 0 plus E epsilon c c x c plus epsilon c b x b plus epsilon c d x b, and similarly ln gamma d is what? Ln gamma d 0 plus epsilon d d, which is, these are self interaction, okay, xd plus epsilon d b xp plus epsilon d c xc. Okay, this is very easy to follow. Watch your preview. One thing I tell you, the first one, this is, since we have ignored some terms, okay, it is fair not to write equals to, rather approximately equal to, almost this, because we have dropped some terms. Okay, and then this has been very simple. Okay, this is just, okay, simple expression of gamma b, and we will use this. Okay, number of times, okay? Many times we will use this. And similarly, ln gamma c is similar, okay? One thing is can be mentioned here, ECB, we don't actually need, epsilon CB is actually the same as this one, epsilon BC, that's they are required, here, epsilon BC is epsilon CB, so it is better we write in terms of only one parameter, epsilon BC. Next, here also similarly, epsilon DB is nothing but epsilon BD for the same reason, and this is plus, and this is also epsilon DC is same as epsilon CD, so we actually use okay, just only a few terms, okay, as few as possible, okay, number of terms. So this is actually since these two are equal, we'll use only epsilon BC, okay, only in terms of smallest number of variables, that is epsilon BC, epsilon BD, epsilon CD, so on, and self interaction of course are there, epsilon BB, epsilon CC, epsilon. Don't worry, this is actually one solute expression will be good enough, that can be utilized for any component, okay. So anyway, but this is the expressions, and finally, and ln gamma A is what, as you know, is actually, this is also similarly will be 0, approximately 0, because these are all approximately. So these are the things that I wanted to tell you. Notably, the alternative form of Wagner's epsilon formalism in terms of E, not epsilon, E. These are the E. This is epsilon, this is E. Okay? So in terms of E is what? Log FB. Log FB is what? This time use EBB, weight percent rather than mole fraction. See the change, mole fraction, weight percent. You see, this is about weight percent, and we prefer weight percent expression because our steel composition in terms of weight percent. So directly we can use weight percent. So weight percent carbon. But if it is mole fraction, then we have to convert the weight percent into mole fraction, and it is a little bit of hassle. Similar other terms also similarly, plus EBC weight percent C plus EBD weight percent D, similar. Okay, and again we will give this, and remember there is no such thing as gamma B0 because Hernian activity coefficient, this Hernian activity coefficient at 0 value this becomes 1 because ln FB0 by definition FB0 is 1, so ln 1 of is 0, so out. Moreover, you can follow this way also, ln gamma B minus ln gamma B0. If you take this side, gamma B by gamma B0 is FB. So FB is gamma, this, if you take this side, so gamma B0 is absorbed on the left hand side in the form of FB, so that you can see. And moreover, I can remind you that FB is, don't have to, okay, subscript as mole fraction or weight percent because they are the same. they require. So FB weight percent you write here, but you write FB weight percent, but it is not needed because FB mole fraction, the other variety, is exactly the same as this, and both of them are equal to gamma B by gamma B. So just you can keep it or you may not. If you are interested, you may keep it weight percent, but FB weight percent is just FB. With this, and then what you this E formalism is preferably used in solving steelmaking problems. Steelmaking problems. In steelmaking problems, as we shall see shortly, as we will see shortly. So with this, we have completed this topic or subtopic C is completed. So we have 5. So fourth one is what? Next I will take up the fourth one. Fourth one is what? Let me remove this. Topic this is over. This is over. So actually remove this. Let me give you the fourth one to differentiate between a second 5 conceptual issues I said. 4 actually, 4 maybe, or 5 you may call. So 4 or 5, okay, 5 actually 5, the fifth one I will give you the result. So 4 conceptual issues that are associated with the solution thermodynamics and with alternative standard state or Hernian standard state and what is that called? Interaction coefficients. Okay. To differentiate between a second order derivative, and a second order interaction. And the second order interaction. Okay, this is the let me tell you a few words. Okay, because that is there is confusion among many of us. Okay, that second order derivative of which is actually in the this activity coefficient versus composition relation. This MacLaurin series. If you actually write the full blown, then you will have the quadratic terms you will get. That is second order quadratic terms that will be associated with second order derivative. And it is sometimes termed as the second order interaction coefficient, which is wrong. This we'll see today that if it is a quadratic expression of ln gamma b versus composite xb, quadratic means up to quadratic, not beyond. We are considering linear, up to linear, not beyond. But if it is quadratic, if we consider, then in that case, second order derivative becomes equal to the first order derivative with a negative sign. And hence, second order derivative can be written in terms of first order derivative, And the first order derivative is known as the first order interaction. So there is no such thing as second order interaction. It doesn't exist. But many think the second order derivative is second order interaction. Always. Now, if it is a cubic expression, ln gamma b versus xb, ln gamma b versus xb composition relation goes up to cubic. If we consider up to cubic, MacLaurin series goes to actually infinity. Cubic, if we consider, then it can be shown that second order derivative. Okay, this is actually these are the derivatives. Second order derivative. This I will show you. This second order derivative is not equal to the first order derivative. So second order derivative will be called second order interaction. Then, and first order derivative, as usual, is the first order interaction. This is in nutshell what we are going to see here. So let me remove this first of all. This part I remove. So start. Interaction. There is a widespread confusion over the identity of the second order derivative and the second order interaction. In the activity coefficient, versus composition relationship. Agree? Versus composition. Versus composition. For example, composition relationship. The following discussion will reveal that in a quadratic activity coefficient versus composition relation relation is second order second order derivative which is equal to the first order derivative with negative sign with a negative sign is equal to 5 with a negative sign is a first order interaction. So it's first order interaction coefficient. Interaction coefficient can add. On the other hand, for a cubic, this is quadratic. Now it is cubic. Quadratic, okay, as I said, second order derivative is first order interaction, not second order interaction. But here, second order derivative is second order interaction, and first order derivative is first order interaction. So in the cubic, quadratic cubic activity coefficient versus composition relation is second order let us remove this. Nice. The second order derivative I'll show you actually just after this text. The second order derivative so is called the second order and the first order derivatives. Second order and the first order derivatives are not equal, are unequal. Accordingly, the second order derivative is called the second order interaction. The second order interaction coefficient. Interaction coefficient and the first order derivative as usual is the first order interaction. Is the first order interaction coefficient. This is the main observation. Okay, this is the revelation. This is the revelation. Means what? Second order derivative is not necessarily the second order interaction. For example, for quadratic expressions, quadratic activity coefficient composition relation, second order derivative is not the second order interaction, rather it is the first order interaction. Even though derivative is second order. This will be shown here, and this is message. And for cubic activity coefficient versus composition relation, of course, the second order derivative is the second order interaction, and the first order derivative, as usual, is the first order interaction. So I will explain this. Explanation is required now. Explanation. With the help of a MacLaurin series expansion. MacLaurin series expansion. For a binary system. Binary AB explanation actually we are giving here. Okay. First we consider the quadratic. This one. Quadratic activity coefficient versus composition relation. Okay. So this we will first consider. So first case and second case, two cases. Quadratic activity coefficient versus composition relation. Okay. What is this actually? Shall I? Let us write here. What is this? Let us write out. ln gamma b. You know, a moment ago, ln is binary. ln gamma b 0 first term plus what? Derivative comes, okay? Del ln gamma b by del xb, first order derivative, okay? At xb is 0, this is the characteristic of MacLaurin series, times xb. Plus next is what? Second order, okay? This binary, half del square ln gamma b over del xb square, second order derivative, again at xb is 0, times xb square. That's it. We are not considering, this goes to infinity, we are not considering up to, actually infinity, this after, depending upon the relationship, this will actually close after some time. Maybe after square or after cube or after x to the power 4, etc., etc. This is possible. Depends upon what relation it is here. Okay, but anyways, suppose we call it actually say infinity. We are considered up to quadratic because this is our consequence. Yes, very good, quadratic. And then we will later on we consider cubic. We stop here. Then what is, because this is actually known as, you might remember, this is known as what? This is what? Epsilon BB. And still it is showing here. This is the definition, by definition is epsilon BB. Del see, okay? So let us write it out simply. Is ln gamma b 0 plus epsilon BB, the interaction parameter, self interaction parameter, xb. This is incidentally is what? Minus epsilon BB xb square. Why? What is this? Minus half xb square, okay? Is why? Note, what is the reason? Note, this is, this gentleman, second order derivative, okay? This second order derivative is equal to the first order derivative with a negative sign. That means what? This can be shown, and this has been shown in a paper that I have already mentioned. I actually published this paper in the metallurgical transaction. There, and I gave you the full reference, and there proofs are there. Okay, maybe we have already discussed this in the class, okay, previously. So anyway, note del square ln gamma b over del xb square at xb is 0 is nothing, is equals to minus what? Del ln gamma b over del xp at xp is 0 . So this is equal to this with negative sign, okay. Hence I have given negative sign. So this is epsilon dB. This is first order interaction coefficient. First order derivative, first order interaction. So this is showing here. So there is no, this actually is not second order interaction. So what you can write here? So further, EBB xb minus xb square. Okay. Thus here, give a star. So there is difficulty writing. Yes, star. Thus here, what is this? ln gamma b versus composition which is xp is expressed in terms of both first in terms of the first order interaction coefficient. First order interaction coefficient del ln gamma b by del xp at xb is 0, that is epsilon dB. So this is first order interaction, first order derivative and first order interaction, that is epsilon dB. This is no second order interaction coefficient is present. This is all about the quadratic. So that means we don't have second order. Although we have a second order derivative, but not second order interaction. This is actually first order interaction coefficient. Absolutely. Now we pick up this next case, second case. What is this? Second case. What is this? 2 cubic activity coefficient versus activity coefficient versus composition relation. Okay, what is this activity coefficient versus composition relation? You start again similarly here only you include xb cubed. Okay, that is okay. Okay, let us write this. ln gamma b is ln gamma b0 plus del ln gamma b over del xp at xp is 0 times xp MacLaurin series we are writing plus half, remember half del 2 ln gamma b del xb square at xb is 0 times xb square plus next is what? Cubed. This is actually factorial 2. In the MacLaurin series factorial comes. This is factorial 2 actually. So then it is factorial 3 means 6. 1 by 6 del cube cubic ln gamma b over del xb cubed. xb is 0 at xb 0 xb cubed. This is up to this. If you consider, then we expect that, or we'll see rather that there will be second order interaction. Now let us see how. Okay, let us go ahead. So what is this? Is ln gamma b 0 plus, as you know, this is known as epsilon bb, the first order interaction coefficient actually. Times xp plus half. This is actually now second order. This is actually this is not equal to this anymore. This is okay. Second order. What is the symbol? Rho b b. Epsilon b b. Rho b b. Rho b b up rho b b. Sorry, up rho b. Up rho b b xb square. This is the second. Plus what are written? 6 minus 1/3. This I will explain. Minus 1/3 epsilon bb plus rho bb xb cubed. This is this actually. Note two things here. You have to note two things. Note two things. Note one first. This is clear. This is rho bb. That mention that. Note one. Rho bb. What is this? Is nothing but second order derivative del 2 ln gamma b over del xp square at xb is 0. xb is 0 is the second order interaction is the second order interaction is the second order derivative as well as the second order as well as the second order interaction coefficient. This is the first point. What is the second point? I am removing this. Okay, and second point is what? Load this. Just I am writing maybe little bit further to the left, and is what? Next point is what? This. Follow this. Del ln gamma b. This can be shown actually, del ln gamma b by del xp, which is epsilon bb. Xb is 0 plus first order. This is the second one. This epsilon bb plus rho bb coming plus del square ln gamma b over del xp square at xb is 0 plus this first order derivative, second order derivative plus the third del q ln gamma b over del xb cubed at xb is 0. If you sum this, you will get what? It is 0, simply 0. It can be shown actually. It can be shown. Just we are not taking up this task now, but this is these 2 points you know, first and second. Not these 2 points, and then this will explain why we have written this term. This term. Okay. Follow this. This is what? This is what? Rho bb. This is what? Epsilon bb. Epsilon bb plus rho bb. What is this? See, this term is what actually? See, this term. This term is 1/6 this term. So first you consider this term is what? Have I made a mistake here? Anywhere? Here I have made a mistake. Plus half. I'm sure. Plus half. Okay. Plus half. I'm very sorry. Plus half. See, follow. This is, I'm showing this simple math. This 1/6 this. Half this is what? These two together with negative sign. This is what? These two what? Together what? Epsilon bb, rho bb. First order interaction coefficient, second order interaction coefficient. Epsilon bb, rho bb. See, this is half times. So it goes to the other side as minus, and it is 1/6. So half times it will be, you have to divide by another 3, factor of 3. So half times and 1/6 times will be 1/3 of this together. 1/3 of this together with negative sign goes to the other side. That's why you get this, because this is 2. And this can be shown also. So with this is these 2 points actually you have to note, and you have this is. So here you can write in the same manner. Thus here, thus you see in the expression you have a second order interaction coefficient, derivative as well as interaction coefficient here. Okay, thus here, like thus here, ln gamma b versus composition which is xp versus composition is expressed in terms of in terms of what? Both first order and second order interaction coefficients. As you clearly see here, this is the expression. First order, second order. Both are showing here. In the previous case, only first order. Okay, but here This is actually both the explained. I have already explained first order and second order inverse. This is okay. Coefficients, okay, very good. And lastly, this is ln gamma b expression. You might be interested in the solvent ln gamma and ln and ln gamma. A trick is, I tell you, I am very sorry that I have removed this. What was the ln gamma previously in the previous case, quadratic? What is this? Minus, just recall this, I have removed this. This is minus half epsilon bb xb square. That you wrote. Now add with this the last term here. In the ln gamma b, in the solute expression, you borrow this, and this was borrowed from the solute expression in the quadratic. Last term there and last term here. This can be proved actually. So just let me check actually if I have correctly written. Yes, correctly written. I have written this. This is expression for ln gamma, and this is our main. Okay. Shall I write here? Okay, here you may. This is. I'm giving you, since this actually shows the second order interaction coefficient for the first time. You are seeing this. This was not seen in the quadratic expression. So I am just boxing this. This is the expression for the solute B in the binary AB. Not bad. This is the highlighted, and you can highlight here also. This is not so important, but this is the here also. This is showing though. You can highlight here also. This is the solvent. I think we have completed the issue or the topic. D is over. Okay, over. Okay. Next is E. So I have to remove this headline. What is this headline? To find the partial molar property for example, partial molar excess free energy. From the integral molar. Property. That is partial, I'm very sorry, integral, right here, integral molar. For example, I have already given, so integral molar corresponding is integral molar excess free energy. In a ternary system. In the ternary system 1, 2, 3. In the ternary system 1, 2, 3. This is the topic. This is not the, okay, this you are used to. You are used to this discussion for binary. You got it. Got this. But for ternary, this is the first time you actually have. So only thing you have note here that only the results will be given. Only the results. Only the results are given. Given derivation being lengthy. Derivation being lengthy. So only the results I am giving. Okay. So remove this now. So remove this. The results I will give you. Remember, partial from integral is the challenging thing, even for binary. And for ternary it will be more complicated. That's why I am giving the result in case you need this. Derivation will be very lengthy. But this is a challenging. Partial from integral, the opposite. Integral from partial is damn easy. Just add them with their corresponding concentration terms. Multiply with, okay, this is very easy. So this, for example, say I'm just repeating, G is X Ga bar plus Xb Gb bar. So I'm just extending to Xc Gc bar, ternary. So you see partials are given, no big deal. G is the integral molar. Partial molars are known. For binary, ternary, quaternary, quaternary, no problem. Opposite is pretty tough. So I am giving you the result, opposite. And that also, you see, if you follow that there is a deduction, derivation in the binary. That may not be very long, but it has actually a number of steps are there. So follow this. Answer. 1, 2, 3. I have given that 1, 2, 3. So 1 is the solvent. Shall I mention this? 1, 2, 3 solvent, solute. Okay. This is solvent. And 2, 3 are solutes. Solutes. Okay. So G2 bar excess. I am giving you the expression for this. Is G excess plus 1 minus x2 del G excess over del x2 at constant x3 plus what? 1 plus 1 minus x3, I'm sorry, minus, right, minus x3 del G x3 del G excess over del x3 constant. This is the for the solute 2. Okay, very good. What is the for solute 3? Very easy. Similarly, just exchange 2 and 3. Exchange 2 and 3, you get the result. This G excess plus 1 minus x3. Wait a bit. Plus 1 minus x3 del G excess over del x3 x2 minus x2 times del G excess over del x2 x3 constant. And what is for the solvent? First one, G1 bar excess is what? G excess minus x2 del G excess over del x2 x3 minus x3 del G excess over del x3 under the constancy of x2. I hope I have correctly written it. Very good. This you actually, the results I gave you without the giving the proof or derivation. So this, and just you may in passing note that for the binary, what was the binary result? So not bad. Recall for the binary system, AB, what is the result? Recall GA bar XS is what? GXS plus XB dGXS over DXA. This you know, so no difficulty, you know this already, and just you keep it alongside, okay? And GB bar XS is what? GXS plus XA, okay, very good, plus XA dG XA over dx. This is the binary result, and see how this is now more complicated under. Okay, so this is, with this we have all completed the 5 conceptual issues, particularly the first 4, and we have completed this, and this is this. But before I quit this, okay, and take up assignment number 11, which deals with problem, steelmaking problem, just one comment or 2 comments or one little bit of discussion, analysis, or okay, some critical situations with respect to standard state. This is additional point, additional note. So please remove this since all over. So just let me write the topic addition. This is all over. You can give a actually here. This is over. Next I take up the assignment. But let me give me 5 or 10 minutes to discuss one point in case you have confusion about the activity, defining activity with respect to varying standard state. Okay, like this. What is this called? Additional point, quite separate from this file. Okay, this is quite separate or same. First 2 actually was related to this. Okay, but don't worry. You consider this. What is this? Now, the dependence of the magnitude of an activity, the activity of a species on the choice of standard state. And if you have any confusion about this, this will be clear with this example. This is choice of standard state. Okay. Standard state for the species. So please remove this. I take an example I take one example that will clarify easily. Okay, but that may be difficult also if you are not sure. Okay, if you have just I have taken water, just taken water in a glass, maybe water. This is water liquid, and here cap this maybe vapor. This is H2O vapor. Okay, vapor. This is equilibrium state. The temperature incidentally is, I have considered, 298 Kelvin. Okay, and you know what is the pH2O? What is the pressure here? pH2O. pH2O, the saturated vapor pressure is 0.03 atmosphere. This is actually saturated vapor pressure. Saturated vapor pressure of water at 298 K. The point is this. Now question about activity. Suppose I ask you whether I answer, I am giving you, try to follow how many ways I am writing the activity. I am writing the activity. H, what is the question? H2O is how much in this system? So simple system. A activity of H2O. We have actually so much of, we have considered so much, read so much of activity, were used so often this activity. Now simple question, what is the H2? So you see, I'm giving you the answer, you follow me. Okay, see, you see, I'll change the standard state and activity value will change. You follow me, and also you first follow. H2O, let me just wait a bit. Okay. H2O in H2O liquid. H2 in H2O liquid, and I'm giving answer. What is activity of it? This is a question. I'm answering. 4 different ways I'm answering. H2O in H2O liquid with respect to where there is activity, there is a standard state. Without referencing the standard state, no meaning of activity. No meaning. H2 with respect to. With respect to what standard state? H2O liquid, pure H2O liquid, as you know, pure H2O liquid as standard state. How much is the answer? Everyone knows this is H2O with respect to H2O. This is pure liquid. This is pure H2O, and with respect to pure H2O. We know also answer is 1. Okay. Hence, I am writing another statement. AH2O in H2O vapor. In H2O vapor. There is another phase, 2 phases. One component H2O, but 2 phases, H2O liquid and H2O vapor. In that phase, what is the H2? Question. If you ask this question to yourself, or I ask you, or you ask me, H2O in H2O vapor phase, actually vapor phase, H2O vapor phase, then you will understand. And you also add here in H2O liquid phase. Okay, of this is H2 is a component, activity of this component. Okay, in this phase, and again same thing in this phase, H2O vapor phase, with respect to, and again always with respect to, inescapable, it's just impossible, with respect to what? Now I am telling you with respect to pure should be written actually unnecessary. With respect to pure H2O liquid as standard state is also one same value. So with respect to the same standard state, but this is the in the vapor phase, question in the vapor, and reference state is liquid, pure liquid water. See class, there is a conflict, but no problem because this answer is correct, and this answer is also correct. Why this is correct? Because this is called phase equilibrium. This equilibrium state. In phase equilibrium, activity of any component is same in all coexisting phases at equilibrium. Activity of a component H2 is equal. This is the second law of thermodynamics. Delta G is 0. And this is called phase equilibrium. In phase equilibrium, this is the rule. This I will write at the end. So anyway, two statements we have got. Now still you consider. Again I am writing. H2O in H2O vapor phase with respect to I am changing. With respect to, that is the topic actually. I change with respect to standard state. What standard state? H2O gas at 1 atmosphere as the standard state. What is the H2O? Forget about all these things. Just ask. I am asking. What is the activity of H2O in this H2O vapor with respect to 1 atmosphere H2O vapor as the standard state? What is activity of any gas? Any gas is nothing but partial pressure. And with respect to 1 atmosphere in the denominator. 1 atmosphere as the standard state. You know, for gases, 1 atmosphere gas is the standard state. Pure. You can consider also 1 atmosphere at the temperature of interest always. So this pH2, you know, number of times you have for gases what you have written. Activity of nitrogen is P nitrogen. So pH2, what is that value? 0.03. Answer is 0.03. See, compare here. This and this. Second and third. So these are same. With respect to has changed and value has changed from 1 to 0.03. Is also 1. Right, nicely. Is also 1. Changed. And also additional statement, hence you write here also. Like this 2, you write here also 2. H2O. Question is, what is the activity of H2O in this liquid phase with respect to 1 atmosphere H2O vapor as the standard state. Choice of standard state is arbitrary. Matter of convenience. I can do that. So H2O in what I am asking? H2O and see H2O liquid phase with respect to again H2O gas at 1 atmosphere as the standard state. Again, as I say, answer is what? Is nothing but you write the answer only. 0.03. Same as is also right this way. Same is also 0.03. These two same because this is phase equilibrium and activity must be same. Another question is this. One question is this with respect to the same standard state. Yes, with respect to the same standard state. 1 atmosphere H2O gas is the same standard state in these two cases. No problem. So 0.03. This is easy. This is difficult because there is a class. It is the liquid phase, H2O in the liquid phase with respect to gas standard state. 1 and root square gas standard state. Similarly here, again here also difficult. Activity of H2 in the vapor with respect to what? With respect to pure H2 liquid as the standard state class. This is. But this we can get the value from the phase equilibrium concept. Here one pair phase equilibrium. So we can just finish up with these few lines in case you have still any doubt. I will try my best. So explanation perhaps I will write this. Okay. Note. First of all, question is raised, why these two are same? Why these two are same? Because phase equilibrium. Why these two are same? For the same reason, phase equilibrium. So that I am writing. Note. Note the activity of any species. Activity of any species, which is H2O here, of activity of any species with respect to the same standard state. With respect to the same standard. This sometimes students forget. This sometimes students with respect to the same standard state. I am showing you. This standard state and again same standard state. Then result is same. Activity is same. With respect to the same standard state. I repeat, student forget this. With respect to the same standard, they remember any species with respect to the same standard state is equal in all coexisting phases at equilibrium. This is called principle of phase equilibrium. This is the principle of phase equilibrium. This is the principle of phase equilibrium. That's why this activity is same. Okay, but one might underline with respect to the same standard state, which students tend to forget to specify or to understand. So this. So if it is not maintained, different standard state, the result is different. Okay. So explanation may be not bad. Explanation not bad. You know all this, but just in case. Explanation is what? Take this example. I in alpha phase is I in beta phase under equilibrium. Phase equilibrium. I is H2O for us. Alpha is liquid, beta is vapor, gas. Okay, I is alpha. What is this? The second law is what? The second law, okay, this. The second law says what? Achha, I am writing. At equilibrium, GI bar alpha is GI bar beta. From where? From the second law. From the second law of thermodynamics. What is that? Delta G is 0. Now when we apply to phase equilibrium, becomes this is the delta. Product minus reactant means it. No problem. Both are equal. This. Now couple with this, you get this result. And couple, so this is one equation, and coupled with this and consider coupled with this the famous relation. What is the famous relation? I am writing this side. Gi bar is Gi0 plus RT ln. That's hello. Just check if it is RT ln AI is okay, there. You see this noticeable? Last
Yes.
line, last.
Yeah. Noticeable.
Is okay. Still space is there.
Mm-hmm.
A little bit, or almost last line.
Yes.
I have some space still left. Can I write?
No.
It's better not to write.
It's better. Go up. It's
Thank
better.
you. Thank you. So, and coupled with this relation, this will tell you. See, these are same. See, follow. Gi bar shows to. So what I see? Gi bar is same. So if you for giving Gi bar, if Gi0 changes, AI changes. Or conversely, if Gi0 doesn't change, means same standard state. Underline where with the same standard state, Gi0 doesn't change, then the result AI doesn't change. Activity is same. So you often say equilibrium activity are same. Activity of a component is same in all phases. But this is a loose statement. You have to say activity of a component with respect to the same standard state is same in all phases. If you change the standard state, then activity is no longer same. Okay, clearly where the example is here, these two, second and third. See, activity has changed from 1 to 0.3 because we have changed the standard state from this to pure water liquid to H2 gas 1 atmosphere. This I wanted to tell you. Okay, so with this we have completed our discussion in this phase. Now we'll take up next, because it's over, all over. Next assignment number. Next assignment number what? 11. So this actually we start this 11 will start, but let us since I need some space. See, I am removing this. These are already has been already staying on for many days. So we have not changed this. These are no longer required because we remember all these things. Okay. So I remove the whole thing. Okay. Remove this. So I start from this. Rather. So I don't have to, because we will now solve problems. Okay. Assignment problems. So maybe I will have to clear. Should be clear so that I get more space, because these problems are lengthy and data. So actually, please have some patience. Let me remove this. These are not difficult. These are actually very fresh writing, so it will be removed. Very easily. So thank you. So it is time to start this one. Okay, this is the assignment 11. Okay, very good. Now we are all set to start this. So first, sorry for delay. Just assignment number 11, steelmaking problems. We'll use interaction coefficients concept, okay? And one weight person Hernian standard state and Hernian activity coefficient. Okay, this we will use, and the interaction coefficient, this relation, that Wagner's E formalism, that we will use. This. Let us see and start. Problem 1. What's the right? I am right here, right hand side. Problem 1. What is this? A BOF steel containing 0.38% carbon is in equilibrium with a slag in which the activity of silica which you may call it a Raoulsian activity, silica is 0.004. Okay, near the end of the glowing period. Near the end of the glowing period. The glowing period, calculate the weight % silicon dissolved in the steel. Temperature is 1600 degrees centigrade. It's actually 1873 Kelvin. So this is the problem. Reference. This problem is taken from, I presume, actually, I'm not 100% sure, but almost certain, A.E. Morris. This I gave you. All problems, in fact, all problems, these 9 problems we will discuss. A.E. Morris. Achha, I'm writing here. A.E. Morris. To check. You have to check whether it is correct, okay? But anyway, I think is A. Morris, okay? This is the, okay, the data I will give you when I solve. Solution is the problem. Solution. let me sketch this. Let me sketch this problem that will help you here. This is your OBM or BOF. OBM is your basic oxygen furnace. We call it OBM, bottom blown process. So here is the bottom blown. What you are blowing here? What you are blowing here? Let me oxygen gas. Oxygen actually. Oxygen gas. O2 gas. You have what metal phase? What you have metal phase? Iron, of course, the main solvent. Then you have, of course, you have silica, is there silicon, and since oxygen is there and is given here, 8% silicon, or carbon is there. There are others also, but let us simplify the problem. This problem is simplified, but if you can solve this problem, you can problems with more components, no problem. This is the metal phase. This is the metal phase. Metal, liquid metal, and over here, over which what is this called? Slag. Slag contains silica, SiO2. SiO2. Not only that, there is other slag. Underscore means impure. Okay. These are also I should have underscored. Silicon, carbon. These are impure. All impure. Slag. SiO2 is there. Which else possible component in slag? This is actually basic slag. Lime, calcium oxide will be there. Some APO will be there. But our interest is on SiO2 slag phase containing SiO2. And what outcomes? What goes out? CO gas. Okay, CO gas. CO gas. It may be CO2 mixture, but essentially CO, pure CO. And oxygen is always negligible. Okay, oxygen potential of a CO2 mixture is negligible. So CO gas mainly I am writing. What else if you want from this? This is OBM, OBM process. Okay, what else? No, I think this is I have all described. Only temperature I have not mentioned yet. Temperature you give somewhere. Temperature on this side. You utilize this side. 1873 Kelvin means 1600 degrees centigrade is steelmaking temperature typically. So this solution. So for the solution, you will actually first let us arrange the data. Follow with me. Silica. Give me one. Data. Silica solid in the cristobelite form. Solid crystal. There is another is quartz form. Silic cristobelite. Goes to silica liquid. Silica solid to silica liquid. What is the delta G0? I should write somewhere, somehow. Delta G0 is what? 9581 minus 4.81 T, because T joule, T joule, one data. Let us estimate, start from that. Next data is what? Silicon 1 weight% in liquid iron. You are familiar with this. 1 weight% liquid plus oxygen gas is SiO2 solid, means cristobalite. I will not write anymore. Sorry. Delta G0 is what? Actually, let us have some space here. Okay, that don't much space. So solid. Delta G0 is what? Right, nicely. Delta G0 is minus 83340. Minus 833,400. Then what? Plus 229.5 T plus 229.5 is not this is 5 229.5 T 5 T joule. Joule you have to write. Joule. Okay, no problem. Joule, okay. Third is what? Is what? Carbon, graphite, carbon, solid. Means which form? Graphite or diamond? Graphite or diamond? Graphite or diamond? Graphite. Plus half O2 gas. This is carbon solid, in fact, carbon solid. Half O2 gas is but solid, but which form is this? Is because carbon graphite and carbon diamond don't have the same energy, standard energy. So CO gas, again delta G0. This is like last assignment 7. Only thing these are in solution, and moreover you have actually solution phase, slag metal phase present, and gas phase, 3 phase equilibrium. Delta G0 is what, sir? Delta G0 is CO gas minus 114,390 minus 85.77 T. Sorry, T joule. This is fine. Very good. This is fourth, maybe the last one. Fourth is carbon graphite again. Carbon graphite goes to carbon 1 weight% in liquid iron. Delta G0 is what? Remember, I actually discussed this. Second topic, 5 topics. Second topic, this was how to find delta G0. Okay, this one. I said this is you can consider this is a change of standard state also, or the chemical reaction where carbon is dissolved from the say gas mixture, or say which is equivalent to a certain activity of carbon with respect to graphite and dissolving the liquid iron. So this anyway delta G0. How to find delta G0? I gave you an outline. Now the data. So if you can carry out experiment, you will find the data yourself. Okay, maybe I hope actually you will also try. Okay, when you have some your project work. Okay, delta G0 is what? 222,594 minus 42.263 joule. Okay, this 4 data you have given. If you just rearrange them, and so that you can end up with this final one, silicon. This underscore I am giving actually. Silicon. You may give this or you may not give, but silicon 1 weight% choice in liquid iron. And this stuff in liquid iron plus 2 CO gas goes to SiO2 liquid, SiO2 liquid, and plus 2C. This is also 1 weight%. in liquid iron. I tell you what, sometimes it is written very short, just 8%. 1 weight% in liquid iron not written. 8% in liquid iron means 1 weight% Hernian stainless steel. Okay, this is. Or sometimes just 8%. Okay. So, but I've written actually since it's the initial, I hope it's 50 minutes or so.
1 hour 41 minutes gone.
Okay.
Still have 20 minutes.
Okay. This is this. Okay. So what is the delta G0? If you manipulate this, I am helping you. You check yourself. You will check yourself. Okay, I am giving you. Check yourself. Delta G0 will be like this. It helps you how to find this. This data I am manipulating 9, but I am showing how it is manipulated. 95. How manipulated? I am showing you. 9581 minus 833400 plus 2 times, let's write here, plus 2 times 114 390 plus 2 times 22594. This is, see, this is actually, this is, remember, this is delta H0 part, this is minus T delta H0. So delta H0 I have grouped them together, so I get the resultant delta H0, and then what I have plus about the delta S0, T delta S0 coming, plus minus 4.81. You do yourself this one, I am doing here, showing you, just in case you have doubts, you will actually check with this. Plus 229.5 plus 2 times 85.77 minus 2 times 42.26. 42 times 26. 42 times 26. If you do this, then tidy up, get the result minus 549851. This is the delta H factor, plus 311.71 T joule. Now what you will find, those delta G0 is obtained. So what you will find next? Next is, right here, okay, right, delta G0 for this, since it's single reaction, I don't label which reaction. Delta G0 1873 will be how much? You find this 1873 here, substitute and get the value 33982 joule. This gives you K equilibrium constant is how much? 18. Give here. K is what? K 1873. K 1873. How much it is? 0.113. Okay. I am very sorry. 0.113. Sure. 0.113. How you obtain? From, recall, delta G0 is minus R T ln K. You cannot forget this. I could forget this. So I am repeating from this. 0.113 equilibrium constant 1873. Next is activity of product by reactants at equilibrium. That is right. What are the products? SiO2 liquid and these 2 carbon, and reactants Si and 2 CO. So I will write, but note here, This is actually not like assignment 7. They are all were Raoulsian standard state. The difference between problem, assignment 7 problems and these problems, there we dealt with all Raoulsian. Then another chapter came 9, solution, that is also. But this is, they are actually 8% standard state involved in chemical reactions, not maybe the first time, okay? So what, I'm specifying it. So what you write, actually, first of all, you write what? What you write, H SiO2 or A SiO2? Since liquid means the liquid silica is the pure liquid silica is the standard state. Actually, one thing very important. Here these means what? These refers to the standard state. Standard state. Gas is what? Standard state. One means 1 atmosphere gas as the standard state. This is liquid standard, pure liquid and standard state. And this is 1 weight% in liquid iron. It's Hernian weight% standard state. And these delta G0 coming out of this consideration. Okay, and now at equilibrium, so you specify this. It is a mixture. It is not actually homogeneous. It is heterogeneous. So this is what type of standard state? Raoulsian. Liquid, pure liquid though, but Raoulsian. Pure solid also Raoulsian. Pure liquid. This is what? Hernian. What type? Weight%. I am not writing this. Clear weight%. This is likewise, this is Hernian standard state. This is likewise gas. Gas means 2CO gas you have used. This is actually the Raoulsian means 1 atmosphere pressure. 1 atmosphere CO is the standard state for this. So Raoulsian. If you have identified them, then properly write here equilibrium constant. Now careful, cautious. So here, what is this? What symbol you will use? This is Raoulsian ASiO2. ASiO2 times what standard state? Hernian. Okay, weight%. So H, C, and weight% type, not mole fraction type, H%. In fact, we will use in all cases weight% type. Okay, so HC square. That's one thing I have already told. All problems will be from AE Morris. If I forget, okay, please, okay, alert me. Okay, I will not forget at the end. But beforehand, I admit, I acknowledge that these problems are taken from Morris. These are also unsolved problems. So this is just the problems are given. The solution answer also I didn't know. So, but I think I have done correctly and quite correctly. These problems are very good. Anyway, go ahead. This, what is this? Hernian. Again, you write similarly H, SI, weight%. Remember, once more, repeat. These are referring to the standard state. What is the actual physical state? See the problem. Read the problem or figure. There you see in which state it is there. Solid, liquid or gas or what, etc. etc. That you will see. Says carbon here. Here in the liquid metal. Metal means liquid. These are liquid metal, liquid stuff. This is liquid metal phase. But it is here 1 weight% in liquid iron. Okay, this is also specified liquid iron. So be careful. HSI, then what it will be? Tell me. Raoulsian activity of CO. So simple that I will not write directly the answer. PCO square. And also, I always insist that you write an equilibrium, so that you don't have any difficulty. This is connected to equilibrium constant, so equilibrium activities. Now substitute the values. ASiO2 fortunately is given to you point, see, activity which ASiO2 I have written perhaps in bracket, ASiO2 0.004. The substitute this. Point HC, I tell you what, HC weight% is what? I give a bracket. HC weight% is what? I tell you what is this? This is what? HC is what? How do you write this? HC square. HC is what? Tell me. HC. Hernian activities. Hernian activity coefficient times weight percent. FC. FC weight percent will you use? Don't have to. FC weight percent or mole fraction same. So just don't have to worry. FC subscripting is difficult here. FC, but FC. But remember, quickly, very quickly. So FC. You write that. HC is FC weight percent or FC times weight percent carbon squared HC squared. Okay, so square here. Okay, HC square. Then HSI similarly FSI times weight percent silicon. Remember, Hernian activity coefficient times the concentration. Like Raoult's activity coefficient times the concentration in case of solution. Okay, so Hernian loss FSI. So this is actually this PCO is how much? PCO, which gas it is? Almost PCO is anything is given here. Means all PCO alone single. If you consider CO2 small or negligible, this is 1 atmosphere square perhaps. Okay, I will yes. This is 1 atmosphere. 1 square. 1 atmosphere. Open to right here. PCO is what right here? PCO is 1 atmosphere. Actually, some CO2 is there, but since for simplification, you got PCO is 1 atmosphere. Open to atmosphere. When the system is open to atmosphere, then pressure is 1 atmosphere. Open to atmosphere. So that's why open to atmosphere. Okay, very good. So this is the thing. Okay. So now we will see what you will write here. Or let us do one thing. Or so by the way, will you take a log on get this or this side or FC weight percent C squared by FSI weight percent silicon is what? How much it is? This is how much is what? 0.113 divided by 0.004. Let us see if I have made any change. Okay, 0.113 value. Acha. Then what else? Don't you have any? 0.03 weight percent in equilibrium. So carbon is 0.0. It is given. Carbon is 0.03%. Weight percent carbon is 0.3. It is given. Weight percent carbon is 0.3. And your question is weight percent silicon is how much? Calculate the weight percent. This is a question. So this is no okay, very good. So you please put here. I'm sorry. Weight percent carbon here. Put here. 0.3. 0.3 square. So I remove this. 0.3 square is how much? 0.3 square is 0.09. So this will come along with the 0.0 on the same side as the times 0.00 0.09. Okay, this is okay, very good. Now take a log on this, or unless you take a log, you will not be able to. Or 2 log FC. Remember log activity coefficient, Hernian activity coefficient composition relation we are discussing. Okay, Wagner reformulation. So that will be used here soon. 2 log FC minus log FSI minus log weight percent silicon is log of this log of this gentleman 0.113 over 0.004 times 0.09, and nice. What this value is actually, I tell you, just this value is calculated as 2.50. You check always this calculation. So this now here just separately now just keep it here, hold it. Log FC is what? Log FC, please tell me. Log FC, Wagner formalism. Wagner's E, not epsilon. We are using E. E formalism. What is that? Log FC is today only. Tell me. E C C weight percent carbon. This is a ternary system, the way we have seen, okay, plus E C silicon weight percent silicon plus E C oxygen weight percent oxygen. Okay. Now about this silicon percent oxygen. Very good. Okay. Weight percent oxygen, actually, if I tell you what is the reason that weight percent oxygen is
1 hour 57 minutes.
Okay, wait a minute. This is okay, thank you. Weight percent oxygen is since oxygen. I'm very sorry. Weight percent oxygen is not included here. So oxygen is negligible. So it is iron, silicon, carbon. I'm very sorry, unnecessary. See, already ternary. 1, 2, 3. So how many solute? This solute and this solute. Effect of carbon on carbon, self interaction. Effect of silicon on carbon. I'm very sorry, unnecessary. I'm complicating. Okay, very good. So what it is? ECC data given to you. ECC is given to you. What is this value? ECC is 0.22. 0.22. Weight percent carbon is how much? 0.3. 0.22. 0.3. It is right here somewhere. ECC is 0.22. Given. These are given, right? Given data given. Quickly. ECC is 0.22. What else? ECC quickly. 0.22. This is done. Log FC. EC weight percent. ECSI is what? I am not writing. Okay. I duplicating it. ECSI is what? How much? It is 0.1. 0.1. Okay. Weight percent silica. And what is log FSI is what? Log FSI quickly. Similarly, right? Log FSI is here. This is done. This you write. How much time you told me? Papu? You told me how much time?
1 hour 59 minutes gone.
I don't have time. This is ESI weight percent silicon times ESI carbon weight percent carbon. Again weight percent carbon. This is known quantity. How much? 0.3. Weight percent silicon is the unknown quantity. Cannot. This is the data. Interaction coefficient data. ESI is 0.32. 0.32. Okay, happy? 0.32 and okay. 0.32. Log FSI is 0.32 weight percent silicon. ESI carbon is what? This is also given. This is also given to you. This is another data. 0.24. 0.24. Right nicely. I am not writing here. Okay. Unnecessary. Here I the writing on here. So this data. This is called interaction coefficient data. These are given. Okay. So if this is given, how much it is coming in here? So will you write or you write start quickly or take from here or 2 log FC 2 times log FC is what? 0.22 times 0.3 is how much? 0.66. This plus 0.1 weight percent silicon Happy? Okay. Very good, very good. Then next term, minus log FSI is how much? Minus 0.32 weight% silicon. Happy? Minus, and there's still another term. This is 0.72 means minus 0.072. So, and there is a minus on it. Are you sure? Minus 0.072, correct. Then what here? Minus log weight% silicon. Minus log weight% silicon. Here is how much? Equals to 2.50. And if you little bit tidy up, you will get this relation. Minus 0.12 weight% silicon. Just get them together. What percent? I'm done, almost done. Minus log weight% silicon. Still
2 hours 1 minute gone.
no, still here. Log weight%. I'm done. Is this last line 2.44? This is our 2.50. Careful. 2.44. Now this is actually one unknown, one equation. So trial and error, iterative method. If we do this, weight% silicon will turn out to be, this is the weight% silicon, is 0.0324. Is 0.0324. Answer by trial and error, by iterative method. Iterative, this iterative method. Thank you. This is the answer. So answer is 0.0324. This is the silicon at equilibrium. Thank you very much for your attention and for your interest and for your sincerity and for all these things. For taking all the troubles and for this interest and cooperation. Thank you very much. See you next class. Bye. Is okay?
You do.